I'd like to start by once again thanking the folks at Oak Ridge and also NERSC and Berkeley Lab for hosting this session and basically providing all of the mechanics that are needed to get this going. So I appreciate that on behalf of NVIDIA. And my name is Bob Cravella. I'm on the solution architecture team at NVIDIA, and this is a continuing session in our ongoing series on CUDA training. I'd like to pause for just a second to find out, Helen, is it possible to start the recording now, or have you done that already?
I already started, Bob.
Great, thank you. So what we're going to be doing today is shifting gears a little bit. In the past two sessions, we have looked at, as I like to say, what is needed to write syntactically correct CUDA code that gives the correct answer. So we were looking at CUDA C++ primarily from a language perspective, from a hello world perspective. What are the basic syntactical elements and how do you write a complete program and so forth. We weren't spending that much time yet thinking about performance. But of course, the reason that people use GPUs is all about performance. That's why GPU computing is interesting, is because it has the opportunity, offers the opportunity to make your codes run faster. Now, when it comes to performance, a pretty common suggestion or advice that you will hear is to use a profiler. In fact, we're going to be, in a later session, we're going to be talking about a methodical approach to performance analysis and optimization for CUDA codes. And we're going to promote, at a high level, we're going to promote the basic idea of analysis-driven optimization, which uses a profiler in a cyclical process to Pareto performance limiters to your code and then sequentially address those performance limiters in order to improve the performance of your code. So that's a fairly methodical approach. It uses a profiler and it has a variety of techniques associated with it. However, if you only use that methodology to address performance issues in your code, you might be making the same mistakes over and over again. There's a trade-off between what level of performance knowledge do you want to have in your head as a CUDA programmer and what level of performance optimization do you want to refer to a later process. In other words, after the code is written, then start to address performance issues. What I'm going to suggest in these next two sessions is that there is a certain amount of architectural knowledge of the GPU which will assist you to inherently write code on the GPU that is performant. There's a trade-off here because we could address any number of topics that might make your code more performant and try and put a huge amount of emphasis on the learning side of the equation as opposed to the analysis side of the equation for performance improvement. And so I'm sort of arbitrarily drawing a line for now and saying in the next two sessions we're going to address the two most important concepts for delivering predictably good performance in a CUDA code. The two most important optimization priorities for any CUDA programmer. And I'm going to suggest that these are things that are appropriate for a CUDA programmer to have lodged in their memory bank so that as they write code, they know how to write code that's going to run predictably fast. Now, this doesn't address every possible performance scenario, but it makes sense, I think, to take the two most important objectives and get those into your process of writing code as opposed to deferring the responsibility for performance to a later time, in other words, analysis-driven optimization. So that's the approach that we're going to take. In order to do that, in order to expose those two most important objectives for any CUDA programmer from a performance standpoint, we're going to take a look at GPU architecture. Whenever it is time to optimize a code, it is very often the case in computer science that the architecture of the machine you're running on matters. We haven't spent much time talking about the architecture of the machine so far in the GPU. We've talked about a few architectural concepts like the fact that the GPU is an appendage to the machine and we have to manage data movement to and from the machine. But from a performance perspective, we really haven't paid attention to architecture at all. Now we're going to take a look at performance, and in order to do so, we're going to start with a brief treatment of GPU architecture, and we're going to look at the architectural motivation, why these two performance objectives matter, how they come about as a result of GPU architecture, and what we can learn from the architectural behavior in order to drive our understanding of how to write predictably fast code. So we're going to do that over the next two sessions, and in the first session today, in the performance or the CUDA optimization part one, we're going to take a look, first of all, at GPU architecture. It's not going to be a terribly in-depth treatment of GPU architecture, but it will be enough to set up the concepts that we want to learn. And in this first session today, we're going to be focusing on the first of the two performance objectives, which is to expose enough parallelism. Now, exposing enough parallelism is a concept that doesn't immediately lend understanding. It doesn't immediately convey understanding because we have to understand what it means to talk about parallelism in the confines of a GPU architecture. However, from a programming perspective, we can translate that statement that our objective is to expose enough parallelism for the machine to be able to run efficiently. We can translate that to a much more simple and direct statement, which is understandable, presumably, for people who have gone through the first two sessions, the last two sessions. And that translation of the statement I'm going to make for you is, instead of saying we want to expose enough parallelism, we want to do that, but in a way that should be palatable and understandable for people who have just the syntactical knowledge of CUDA that we've acquired in the last two sessions. I'm going to translate that and say we want to have a lot of threads. So if you don't take anything else away from this next hour, if you take away the idea that when you write CUDA programs, you want to write algorithms that can make use of and in fact run a lot of threads, you will have absorbed more than 50% of what I'm going to try and convey in this session. But we want to give you a little bit better understanding of why that is, and in order to do that, we want to start with GPU architecture. So in this session, we're going to be exposing some concepts of GPU architecture. We will briefly touch on the Kepler, Maxwell, Pascal, and Volta architectures. For the purposes of the folks on this call, I assume that the only architecture that's really very important is Volta, because that is the architecture that's present in the Oak Ridge machine in Summit. Okay, but if you're working on a different machine, there may be another architecture, and some of these concepts may vary slightly. But in general, the concept of exposing enough parallelism, which is what we're going to cover today, and making efficient use of the memory subsystems, which is what we're going to cover in the next session, is applicable across GPU architectures. It doesn't vary that much when we talk about Kepler versus Maxwell versus Pascal versus Volta. So the differences in architecture aren't terribly important, but we will also be talking about the architecture from the standpoint of operation. How does the machine operate? That will be the second half of our architectural discussion, and we'll need that to set up a very clear understanding of why it's important to have lots of threads. So our first kernel optimization that we're going to be focusing on is launch configuration, which is to use a lot of threads. And in the next session, we will extend our GPU architectural knowledge to understand how the memory subsystems work and what our takeaways are for efficient use of those subsystems as a CUDA programmer. The entire session, the entire sequence of sessions that we're presenting in this series is, of course, focused on CUDA C++, but if you are using another variant, another language binding for CUDA, like CUDA Python or something else, CUDA Fortran, most of these concepts are going to apply in a very, very similar fashion. You'll want to have lots of threads, however you manage that in your binding, in your language binding, and you'll want to make efficient use of the memory subsystems, however that's managed in your language binding. So those are things that are going to be useful for a wide range of language implementations of CUDA. We'll start with the Kepler architecture. So when we build a GPU, it's not a huge spaghetti mess of logic. in fact, a GPU, especially from a programming standpoint, from a GPU programming or from a general purpose GPU computational standpoint, a GPU can largely be defined by something called an SM, a streaming multiprocessor. An SM is essentially a building block for a larger GPU, and the SM defines the GPU architecture. It defines the characteristics and the behavior and, in fact, the instruction set that that GPU will understand. And so when we build a large GPU to a first-order approximation, we do that by dropping a large number of SMs on the die. When we build a small GPU of a particular architecture, we do that to a first-order approximation by dropping a smaller number of SMs on a die. And it makes a smaller die and therefore a smaller GPU. And as we'll see, this also has implications for performance. Smaller GPUs with fewer SMs typically have lower performance. So the SM is the building block. It's effectively a cookie cutter approach to building a GPU, is to slap down a bunch of these SMs. There are some ancillary or peripheral logic that is needed. For example, we have to have things like a memory interface. And as we'll see, there are other things that are outside the SM that are important to us as a CUDA programmer, like the L2 cache. But for the most part,
Comienza a comer porque esto va a durar como hasta las 2.
For the most part, we're going to be focusing on the SM architecture and understanding how an SM works, because that's where instructions get issued and retired. And that's going to drive or guide our knowledge into this idea of wanting to have lots of threads to expose a lot of parallelism to the machine. So our focus is on the SM. So this is a Kepler SM pictorially represented, as well as some statistics or measurements of the SM on the left-hand side. There are what are called 192 SP units or cores. So when you look at marketing literature relating to GPUs, especially NVIDIA CUDA-capable GPUs, you will often find the word core used as a aggregate description of the machine. How many cores does it have? And GPUs with more cores are generally considered to be larger, more expensive, and more powerful than GPUs with smaller numbers of cores. Since the number of cores per SM is fixed, a GPU with a larger number of cores by definition has a larger number of SMs, and a GPU with a smaller number of cores has a smaller number of SMs. Now, those statements and many of the statements that we'll make during this session apply to a particular architecture. So when we compare Kepler GPUs amongst each other, those statements are generally useful and applicable. It may or may not be the case that a Maxwell GPU or a Pascal GPU or a Volta GPU with a smaller number of SMs is more or less powerful than a Kepler GPU. Okay, we have to be more careful if we're going to make those kinds of comparisons. But from an architectural perspective, if we stay within an architectural generation, then most of these numbers here are fixed per SM, and therefore, since we build a GPU out of a number of SMs, we can immediately identify how many cores, for example, are in a particular GPU. The SP units or cores are designed primarily to do single precision floating point work. They are not a complete core. If you talk to a person who's a CPU designer and you use the word core in the CPU design parlance, a core is a much more complicated animal than what we're describing here as a core. In fact, the comparison from a CPU core to a GPU might be best made comparing it to a GPU SM. A CPU core has a variety of capabilities. Typically, it has the ability to execute various kinds of instructions. It has typically a register file associated with it. It has instruction fetch and dispatch mechanisms and things of that nature. In fact, a CPU core, generally speaking, can support one or more threads of execution. Using the word thread there, the way that we would use that word in a language like C or C++. What does it mean? What does a thread mean? So when we compare to a GPU, a CPU core might better be compared to an SM, not a GPU core. A GPU core is much more like an ALU, an arithmetic logic unit. It's actually even simpler than an ALU. It does less than what an ALU does. In fact, the SP unit or core here basically does just a very small number of instructions. It does floating point multiplies, floating point adds, and floating point fused multiply add operations, and not much else. Now, having said that, those all apply, in the case of an SP unit or core, those all apply to 32-bit floating point operations. If we switch to 64-bit floating point operations, double precision in C or C++, for example, a double quantity, then we are going to use a different functional unit inside the SM, inside the GPU, to execute those instructions, and that would be called a DP unit. And we see that an SM typically has a different number of DP units compared to SP units. There are other functional units inside an SM as well. The most commonly referred to and most prevalent of these would be something called the load store unit. So I would generally describe the GPU as a load store architecture. Purists will be able to point out that that's not a strictly true statement. You can find GPU machine code instructions that access memory directly and perform an operation, but those are rare. By and large, when you execute operations, for instance, a 32-bit floating point multiply on a GPU, the first thing that you do is execute instructions that will load those operands into the register file, and then you execute an instruction that does a multiply, operating entirely within the register file. And then when you want to save the results, you would store it using a store unit, a load store unit. So in that simplistic description that I've just given you, the GPU is very much like a load store architecture, and therefore a load store unit is broken out as a separate functional unit, managing most of the traffic that goes to and from memory. The SM also has warp schedulers. We'll talk about a warp scheduler again. What does it mean? But a warp scheduler, in a nutshell, is the instruction dispatch unit for the SM. And so the warp scheduler will decide when and which instructions get executed, and it will decide that on a warp by warp basis. Now, warp is a word that we haven't heard yet, but we're going to define warp in about 2 or 3 slides, so just bear with me, okay? In the case of Kepler, warp schedulers are dual issue capable. This isn't terribly important. It's just a factoid at this point. But dual issue in a nutshell means that in some situations, a warp scheduler may be able to issue 2 basically adjacent instructions from a single instruction stream in a single clock cycle. That's what dual issue means in this context. And as I mentioned, when we build GPUs, we largely, to a first order approximation, build smaller and larger GPUs by bundling together smaller and larger numbers of SMs. Other things will vary as well. As we build larger GPUs on the NVIDIA side, we have very often pair it up with more memory. And in some cases, for some architectures, we may even switch memory interface styles or memory architectures to give higher performance. In the case of Kepler, this is a pretty ancient architecture nowadays. Kepler came out in the 2012 timeframe. The original Titan machine, not the original, but the Titan machine at Oak Ridge that had GPUs in it had Kepler GPUs in it. So that's a 2012 era machine. And we had various different processors or members of the Kepler family. The ones for GPU computing typically are Tesla branded, and the Tesla branded members included members like K20, K20X, and K40. There was also a K80 in this generation. So let's keep moving. So that's the Kepler SM, and when you build Kepler GPUs, you put more or fewer of those SMs on a single die, along with other things like memory controllers and L2 caches and things of that nature. So when we go forward to a Maxwell or Pascal generation GPU now, hopefully some of this terminology is not new. We've just described it on the previous slide. So in the case of Maxwell and Pascal, we have some similarities between those 2 different GPU architectures, but as we'll see, the similarities are a function of what we call the compute capability. So the compute capability is a finer subdivision of an architecture. A Pascal architecture, for example, has a compute capability that starts with 6. But Pascal architecture GPUs have compute capabilities that include 6.0, 6.1, and 6.2, and maybe others, but I think that's it. So that means there's at least 3 different design variants within the Pascal family. And so when we build a Pascal GPU, for example, and this is true for Kepler as well, it's true for Maxwell as well, it's true for most of the GPU generations we're going to run up against. When we build a particular GPU, it's generally not enough to say that it's a Pascal SM. We have to be specific about which variant of the Pascal SM. And as we'll see, what we're focusing on in this slide is the Pascal CC 6.1 design variant of the SM. And if we look at the Maxwell generation of GPUs, we will observe that that CC 6.1 SM was architecturally quite similar to a Maxwell CC 5.2 SM. And so what we're describing is those 2 variants here because they're quite similar. In the case of Maxwell, we referred to it as SMM, which was the Maxwell Enhanced SM design. This particular SM design has 128 SP units, so a smaller number of SP units than what we observed in the Pascal generation. And here, in the case of these 2 particular design variants, CC 5.2 and CC 6.1, we observed that they have a very small number of DP units, relatively speaking. So whereas in the Pascal CC 3.5 SM that we were looking at, the Kepler CC 3.5 SM that we were looking at in the last slide, there was a 3 to 1 ratio between SP and DP units. Here we see a 32 to 1 ratio. So that means that for certain GPUs, the ratio of throughput for single precision and double precision can be quite different. And if you spend a lot of time with GPU computing, you'll run into this concept sooner or later. But we have load store units. In the case of the CC 6.1 SM, we introduced a new computation capability called int8. This basically performs 4 8-bit wide integer operations in the single clock cycle or in a single 32-bit quantity, depending on how you look at that. This SM has 4 warp schedulers. Each warp scheduler is dual issue capable. And once again, we build differing GPUs based on a particular architectural generation by lashing together larger or smaller number of SMs, as well as another big variant is the amount of memory attached to that GPU. Okay, this will be our last SM slide, I think. So we can also observe that between the Pascal and the Volta generation, the Pascal variant called Compute Capability 6.0 and the Volta 7.0 variant have a very similar SM design, which we're depicting here. 64 SP units, so again, a smaller number of SP units. 32 DP units, a 2 to 1 ratio now, rather than 3 to 1 or 32 to 1, what we had before. Again, there's a number of load store units. We've also introduced a new computational capability with this this architectural evolution called FP16. So FP16 is a 16-bit floating point format. In this particular architectural generation, so Pascal 6.0, Volta 7.0, it refers to operations that are done using an IEEE 754 variant of 16-bit floating point arithmetic. And from a performance perspective, this can be performed at twice the SP rate. So it's very reasonable as a mental model to imagine that the SP units, called cores, can either run a 32-bit floating point operation per core or 2 16-bit floating point operations per core. The Compute Capability 7.0 SM also introduced another very important evolution called Tensor Core. We're not going to spend a lot of time on Tensor Core in this presentation. However, Tensor Core is a separate functional unit. It has instructions associated with it, and those instructions are basically organized to perform a matrix-matrix multiply operation. On the NVIDIA side, we have spent a lot of time over the past 5 or 6 or 7 years focusing on deep learning and AI computing as an additional space to explore beyond scientific and technical computing. And in that space, in the AI computing space, matrix multiply operations, even low precision matrix multiply operations like 16-bit floating point matrix multiply operations are valuable, are useful. They're commonly used, and optimizing the performance of those can make a significant difference in the performance of the code. And so Tensor Core initially was introduced primarily with that objective in mind. It wasn't introduced primarily to serve the needs of scientific and technical computing, which mostly use 32-bit and 64-bit floating point arithmetic, but it was primarily initially introduced to serve the needs of the deep learning and AI computing domains. Now, having said that, Tensor Core has evolved over time, so there is a generation beyond Volta that we won't talk about called Turing, and Tensor Core has evolved in Turing to take on more capability, and we could presume that Tensor Core could evolve in the future as well. And secondly, because of the great throughput opportunity that exists with Tensor Core, people are motivated to do unusual things, like take an algorithm that was originally running in 32-bit floating point, or perhaps even 64-bit floating point, and try to recast that or refactor that algorithm in a way that some portion of the calculations could be done using 16-bit floating point. This is kind of an odd refactoring, and until a processor came along that offered this kind of dramatic increase in performance for a very specific kind of computational mode, nobody would have undertaken that effort. But as a result of the fact that the Tensor Core offers something like a 5x to 10x increase in the raw computation ability of the GPU for a particular kind of computational mode, namely matrix-matrix multiply in 16-bit floating point. Because of that unique characteristic of the GPU, a number of folks have taken a look at a number of different kinds of code to figure out if they can be accelerated using that capability. So that's as much as I'm going to say about Tensor Core in this session. If there are questions during the tail end of this session, when we have time, we can certainly address Tensor Core more. But it's not a fundamental CUDA programming concept that we want to expose right now. Okay, as you can see, both P100 and V100 are significantly larger in terms of the number of SMs. Previous to this, we were talking about GPUs that were built with maybe up to 20 or 24 SMs, and now we're in the 50 to 80 range. And so this is one of the characteristics of GPU design, is that as we build bigger GPUs, and especially as we move forward to newer generations, we're going to probably be putting more stuff on the GPU die. And when you're building a GPU, putting more stuff on the die to a large extent means putting down more SMs, which by definition or by implication means putting down more cores. And so we're going to be challenged as GPU programmers to be able to make use of all that. And this session today in particular is going to be our #1 strategy, exposing a lot of parallelism, using a lot of threads. That's our #1 strategy to future-proof our codes so that when a new processor comes out that has 100 SMs instead of 80, our code will just automatically, without any sort of refactoring or redesign, and perhaps not even recompiling, our code will automatically expand to fill that machine and take advantage of that new architecture. That's one of the really cool, interesting prospects that are available for a massively multi-threaded programming methodology, which is what CUDA is. And because CUDA has allowed from day one for programmers to specify CUDA kernels that use large number of threads, much larger than what the machine can support at any given point in time, because of that methodology that's built into the CUDA programming model, it has allowed CUDA programs to expand to fill new architectures without any programmer involvement at all. This is one of the really cool benefits of this methodology, and we're going to expose some of the important underpinnings of how this works during the session today. We're about to switch gears into another section of architectural discussion, so I'm going to pause for a moment and take a look at what's in the chat. There's just a few questions. I'll see if I can answer them. I may not be able to. How much different are the Tesla GPUs from consumer-grade GeForce GPUs? So that's a good question. A Tesla GPU has a variety of different characteristics. For instance, I'll just mention a few. It typically offers ECC memory, which you would not find on a GeForce GPU. And there's a variety of other characteristics that a Tesla GPU will offer to distinguish itself from GeForce GPUs. But in this session, we're primarily focused from the programmer's perspective. So what does that mean in terms of what we've covered in the last few slides? Well, what you'll find is that for the two variants depicted on this slide, CC 6.0 and CC 7.0, that have this relatively large ratio, 1 to 2 is a relatively large ratio of DP to SP units, those are typically going to be found in Tesla GPUs. Now, there's some variance on this. If you look at a Titan V, for example, a Titan V is a CC 7.0 GPU. It also has this characteristic 1 to 2 ratio. And a Titan is something that sort of straddles the line between a GeForce and a Tesla in terms of the domains that we're going after. It would be the very high end of the GeForce or consumer domain, and it would be sort of an entry-level processor for people who are interested in doing high-performance computing on GPUs, for example. But nevertheless, the GeForce GPUs typically have that kind of differentiation. So if we go back to a previous slide, if I can do that, we observe, for example, with this other member of the Pascal family, CC 6.1, instead of having a 2 to 1 ratio or a 1 to 2 ratio of DP to SP units, we have the 1 to 32 or 32 to 1 in the other way. And so these are processors, this CC 5.2 and CC 6.0 are processors that would be very commonly found in GeForce family variants. Doesn't mean that they won't find their way into Tesla GPUs. These GPUs depicted at the bottom of the slide are all Tesla family members. But typically, we would choose we would choose these SM designs that have a relatively lower ratio of DP to SP units for the GeForce family, because general purpose graphics processing doesn't require double precision at all. On the other hand, these SP units that we've been talking about serve a dual role when it comes to graphics processing. They're intimately connected to the graphics pipeline when it comes to things like vertex shaders and pixel shaders, both of which execute on these exact same cores that we've been describing and which we're focusing on for general purpose computing. The second question is, can one use the SP, DP, and tensor core units simultaneously? Yes. The answer to that is emphatically yes. You can also use load store units simultaneously. So you can have load store activity at this, or let's say we can have instructions issued to the load store unit in the same clock cycle that an instruction is issued to the SP unit or DP unit in the same clock cycle that an instruction is issued to tensor core units. Some understanding of that hopefully will follow, and if we need to, we'll come back to this question. I'm going to leave it at that, because if we're just using one level of precision, are we leaving throughput on the table? Arguably, yes, but how important is that, or how relevant is that? It depends on your interest and ability to refactor your code. For instance, I mentioned that there's a ratio of 1 to 2 or 1 to 3 or 1 to 32 between double precision and single precision, and so people have, let's say in the HPC space, people have aggressively looked for ways to refactor codes already that might be using double precision to use single precision. This has happened particularly in the molecular dynamics code space, but in other code spaces as well. We could extend that to tensor core, which I've already alluded to already. There are, in fact, were Gordon Bell applicants or Gordon Bell submissions that were basically touting their codes as examples of doing this sort of refactoring, taking a code that might have started out in the FP64 space or the FP32 space and figuring out how to move calculations from FP64 to FP32, perhaps how to move calculations from FP32 to FP16, and perhaps how to move calculations from FP16 to tensor core. So all of those are trends. Okay, so let's keep going now. As I mentioned, we're going to switch our thought process a little bit. In order to switch our thought process and start to focus on an actual execution example, we need to introduce a new concept. Before we get there, let's review what we know already. From a software perspective, we know that CUDA programs consist of a bunch of threads, and those threads are grouped together into thread blocks, and those thread blocks are grouped together into a grid. The grid is a set of all thread blocks that are associated with a kernel launch. And you could also therefore say a grid is a set of all threads that are associated with a kernel launch, because a thread block is nothing more than a group of threads. And so we have a hierarchy on the software side that goes from thread to thread block to grid. And now we have learned something about the hardware side, and so we can start to make some associations between software hierarchy and hardware hierarchy. These should be considered to be a little bit loose, okay? But I'm trying to give you a basic one-to-one connection so that you can start to understand what's going on. I'm giving you a very imprecise description of this relationship, so you should just keep that in mind. Take this with a grain of salt. But nevertheless, we could imagine that a thread is associated with an SP, a scalar processor. Now, I've said already that an SP basically only performs FP32 calculations, and a thread of execution certainly is going to have other instructions in it besides FP32. So immediately this one-to-one thing starts to break down. But on an instruction-by-instruction basis, we can make an association between a thread and a functional unit inside the SM. There is a functional unit, there is guaranteed to be a functional unit inside the SM that executes any given instruction. So if it's a load or store instruction, that would be handled by the load store unit. If it's an FP32, like multiply instruction, that would be handled by the SP unit. If it's a FP64 multiply, let's say, that would be handled by the DP unit. A tensor core instruction would be handled by a tensor core unit. And there's a few other functional unit types that we haven't talked about, what we could call special function units. But nevertheless, if we consider all of those function units in aggregate, for each instruction in the thread, we can find a functional unit in the SM that's designed to handle that. And therefore, we can make a one-to-one correspondence between a thread or the instructions in a thread and functional units that support those instructions. Now, when we get to the thread block level, when we have multiple threads executing, we can say multiple threads in a thread block execute collectively together on an SM. So this is an important concept. Threads in a thread block are not spread across different SMs. They are always resident on a single SM. And for the purposes of this level of instruction, we will say that once they are deposited on an SM, once they begin their life, begin execution on an SM, they remain forever on that SM until they retire, until those threads reach their exit. Okay, so a thread block does have a very strong association with the SM that it is deposited on. SM is the same as multiprocessor here. And that's important because, as we'll see, the SM has resources associated with it like shared memory and L1 cache. We're going to get to those in the second session. Okay, so not today. We won't spend much time with shared memory and the L1 cache in this session, but we will revisit those in the next session. But as we'll see, those resources like shared memory are a per SM resource. They're designed into the SM, and therefore, in order for threads to be able to share data using shared memory, as we saw in our last lesson, it's necessary for the shared memory to be coherent within a single SM. And therefore, we require that all of the threads in a thread block execute together on the same SM. With that knowledge, then, if we know that a GPU is built of multiple SMs, that's how we describe a GPU device, then it stands to reason that if I'm going to take advantage of multiple SMs, I must need multiple thread blocks. A single thread block cannot be spread across more than one SM. So if I have 6 SMs, at least based on what we've learned so far here, I probably need at least 6 thread blocks to take advantage of that. And in fact, what we'll eventually discover is we want more than that, but we're getting ahead of ourselves. So a grid, therefore, presumably your grid, your kernel launch, it specifies more than one thread block, and if it does, then it will occupy the device as opposed to occupying a single SM. We're going to introduce a new concept now because this is necessary for understanding of the machine behavior at a low level. This is a concept that's not immediately evident to a CUDA programmer, and it's not prominent in the CUDA programming model. But it is basically an artifact of hardware design that manifests itself from a programmer's perspective in terms of performance and also to some degree in terms of behavior. And that new concept is called a warp. A warp is nothing more than a collection of 32 threads. We can say that a thread block can be decomposed into multiple warps. A thread block with 32 threads in it has 1 warp. A thread block with 64 threads in it has 2 warps, and so on. And in fact, the organization of those warps is fixed. The first 32 threads will always belong to the first warp. The next 32 threads will always belong to the next warp, and so on. So this is basically another kind of software and hardware hierarchy, but we'll start on the software side. This is now another kind of software thread hierarchy that exists between the individual thread and the thread block level, for example, in the previous slide. And what we're going to observe here in a moment is that a GPU doesn't issue an instruction to a single thread. It always issues instructions warp-wide. So when it issues an instruction, by definition, 32 threads in a warp will execute that same instruction. That's a characteristic of the GPU hardware design, how it works. So we don't issue an instruction to a single thread, and for the most part, we don't imagine that single threads are executing instructions. Instead, we issue an instruction warp-wide, and we imagine that all of those threads are executing that instruction in lockstep. I mean, they are going through the exact same sequence to execute that instruction. They receive the instruction in the same clock cycle. They follow the same set of internal steps to process that instruction, and then they retire that instruction in the same clock cycle. That's what I mean by lockstep execution. Okay. So now what we want to do is understand what is the ramifications for all of this in terms of launch configuration. And I've already given you the answer to this. The answer is we want to have lots of threads, but we want to understand why that is. So launch configuration refers to kernel launch configuration, which is those first 2 parameters in your kernel launch configuration syntax, the triple chevron syntax. So those first 2 parameters are the total number of blocks associated with the kernel launch and the total number of threads per block. So that's our launch configuration. And you could, as we've defined already in our previous sessions, if you multiply those 2 together, speaking loosely, if you multiply these 2 together, you get the total number of threads associated with your kernel launch. In other words, the total number of threads in the grid. And as we've said just a moment ago, giving you the answer before we understand why, we want to have lots of threads. So we want that to be a large number. And now we want to understand why is that the GPU needs to have a lot of threads from a performance perspective. It doesn't require a lot of threads from a functionality perspective. You can write a syntactically correct program that gives you the right answer using a single thread. It will run quite slowly in many cases, okay? But we want to understand in more detail why is this. So, as we've said already, instructions are issued warp-wide, and also instructions are issued in order, so the GPU is not an out-of-order machine. That means that when the compiler emits code and it issues instructions, let's say in a sequence A, B, and C, which I can observe by inspecting the compiled code, when A, B, and C are issued on the machine, let's say with respect to a thread, which is where it matters, C will never be issued before B, and B will never be issued before A. So that's what we mean by an in-order machine. Not all processors have that characteristic. Like, as far as I know, modern variants in the x86 processor family are not always in-order machines. So GPU is somewhat unique in that respect. But we're focused primarily from an understanding of the machine order, the machine issue order, we're focused primarily on a thread. A thread is a sequence of instructions that are designed to be executed in order and that pertain to a single context, in other words, a single set of data. A thread stalls when one of its operands isn't ready. In other words, a thread stalls when we run into an instruction that requires operands. Operands are the input data to an instruction. So if I have a multiply operation, the two numbers that I'm multiplying together, those are the operands. They're the input to the instruction, the input to the math. And a thread will stall if it runs into an instruction, if the next instruction to be issued requires operands that aren't there, that aren't ready. If I want to multiply two numbers together, I better know what those two numbers are. If I don't know what those two numbers are, I can't do the multiplication. And in that case, the machine knows that, and it will not issue that multiplying instruction, and we will say that that thread has stalled. In other words, something else needs to happen before that multiply instruction can begin to execute. As we've seen, the GPU is a load store machine, which means that we can conceptually and in the instruction stream, we separate the loads and stores of data from the actual math or arithmetic that we want to do on that data. And therefore, the memory read is a separate instruction, as are the memory writes. And so the memory read by itself, generally speaking, cannot stall execution. A memory read does have operands. It says, go get me something. That's the input. And the output is typically put it in this register. Okay, so the operand for a memory read would typically be a location in memory. And the result of that memory read would be the data in that location in memory getting placed into a GPU register. That operation basically never stalls. What this means is, another way to say this is a GPU is a fire and forget architecture, which means that you can issue a read instruction and go on doing other work and wait for that read instruction to complete. So the read instruction is what we would call in flight. It hasn't actually deposited its result in a register yet, but it's on the way to getting there. And as a result of that, memory reads don't stall execution. I can have any number of memory reads in a row, and none of them will stall execution because the machine has a large capacity. We're going to imagine, for the time being, an infinite capacity to have read instructions in flight. As we'll see, this is just a concept now. We're going to explain latency in a little bit more detail. As we'll see, latency is hidden by switching threads. I'm going to demonstrate for you exactly what does that concept mean on the next few slides. So latency is hidden by switching threads. Latency is the problem that we're trying to avoid in a GPU. If we didn't care about latency, we could just run everything in a single thread. But unfortunately, when we run everything in a single thread, latency will bite us over and over again. We will have stalls because we're waiting for data to appear. Latency, a very simple definition of latency is the time in between when you ask for something and when you get it. Okay? A latency in a GPU architecture is typically specified in terms of clock cycles. On which clock cycle did I ask for something, and on which clock cycle did the result actually show up? That difference specified in clock cycles is the latency in clock cycles. We could also talk about latencies in terms of wall time, clock time if you want, but as a programmer, we can effectively understand what's going on a clock cycle by clock cycle basis for understanding. There's various kinds of latencies inside a GPU. In fact, nearly anything you do with a GPU has a latency associated with it. We're not going to try and grasp all of that complexity all at once. Instead, we'll imagine just a couple kinds of latency. The latency associated with retrieving data from global memory and the latency associated with arithmetic. Both of these are architecturally dependent. They're dependent on the GPU architecture as well as the memory subsystem that's attached to it. But nevertheless, across GPU architectures, global memory latency is one of the longest latencies that we will deal with. It's typically on the order of 100 or hundreds of clock cycles. In some cases, it might be as high as like 400 clock cycles. We'll get a better understanding of what does this mean in just a moment. Okay. But it's the largest latency that we're typically going to be dealing with. And we'd like to, if possible, we'd like to hide that latency. We'll understand why in a moment. Arithmetic latency, the latency associated with executing arithmetic instructions. In other words, what was the time that I asked for the multiply operation to begin, and when did the multiply result appear in a register? That would be the latency associated with a multiply instruction. The time from when it was issued to when it retired. It's not a single clock in most cases. And that latency is what we call arithmetic latency, and it's typically much less than 100 cycles, like on the order of 10 cycles, or maybe even less. Okay? And so arithmetic latency is also something we will seek to hide, and is generally speaking easier to hide because the latency is shorter. So now we want to ask the question, how many threads or thread blocks should I launch? And the conclusion, our objective, is to launch enough threads to hide latency. We're going to understand what that means right now. There's a question in the chat, if the number of threads in a block is 62, would the threads be executed as two 31-thread warps? No. The first 32 threads in a block belong to the first warp, always. Always, always, always. If I have less than 32 threads, however many I have, still belong to the first warp. If I have more than 32 threads, any of the threads whose IDs from 32 to 63 inclusive would belong to the second warp. If I have fewer than that many, they still belong to the second warp. Is there a rough estimate for the arithmetic latencies? 5 cycles. It varies a lot by instruction. Some instructions, like we have some low-level instructions that can actually estimate a sign, for example, and other types of operations, which might be significantly longer than 5 clocks. And this will also vary basically based on GPU architecture. But 5 to 10 clocks is a reasonable estimate for the instruction latency for many different types of operations, not associated with memory, not associated with load store. Okay, let's keep going. So what we want to do now is look at a specific example. And we want to understand how these instructions get issued on the machine. And in the process of understanding how these instructions get issued on the machine, we will hopefully drive home the point that you need a lot of threads and why do you want or need a lot of threads. So we're going to take a very, very simple snippet of code, which is depicted here on this slide. First of all, we have our canonical, one-dimensional, globally unique thread index. Okay, that's a construct that you should now be familiar with, threadidx.x plus blockdim.x times blockidx.x. That's our index. And our next line of C or C++ source code says we want to take C of IDX. C is presumably an allocation in global memory, a vector, let's say, in global memory. And we're going to take A and B and multiply it together. So this is an element-wise multiplication, storing the result in the corresponding location in the vector C. Okay? There's nothing unique or specific or magical about this. It's just a piece of code that is useful for understanding. Okay? When we compile that code, the machine doesn't run lines of C source code. It runs compiled code, which is machine code or machine instructions. The CUDA machine code has a particular name. It's called SAS, Streaming Assembler, S-A-S-S. And SAS code is the machine code that a GPU executes. And if you're familiar with looking at assembly or machine code for other types of architectures like CPU architectures, you're going to see some similarities here. This won't be a completely foreign thing. But nevertheless, when we compile this code, we're primarily focused now on the multiply operation. When we compile this code, we're going to see 3 instructions. There's going to be more to it than that, but we're going to focus on these 3 instructions in the compiled stream. No, SAS is not the same as PTX. So SAS is the code that executes on the machine. SAS is actually something that the GPU warp scheduler can dispatch. PTX is an intermediate code. It is not the executable code. It's something that exists or lives in between C or C++ source code and the executable SAS code. PTX is an intermediate code, something like LLVM-IR. So it's an intermediate representation of a higher level language prior to its compilation down to the low level language that's actually executed on the GPU. So the instructions that we're looking at here are, they're not really exactly what you'd see, but they were close to what you'd see. You'd see a load instruction, LD is a load instruction, and what this is saying is fetch an element from memory, the location being the vector A index IDX, fetch that value and put it in register R0. The next instruction in the stream is going to fetch the corresponding element from the vector B and put it in register R1. And the third instruction that we're going to focus on is a multiply instruction, which says take the data, the values in R0 and R1, multiply them together, and store the result of that multiplication in R2. R0, R1, and R2 are GPU registers. Okay? Each thread has its own set of registers, and so each thread has an R0, each thread has an R1, each thread has an R2, and so on. They're distinct from each other. So we want to understand how are those instructions actually dispatched. So what we're going to do is look at a two-dimensional plot which depicts on the horizontal axis clock cycles and on the vertical axis warps. We know what warps are. If we have a thread block deposited on an SM, that thread block is logically decomposed into a set of warps. And we've said already that instructions are issued warp-wide. So the warps, we are now the warp scheduler. We are looking at this execution graph. And our objective is to keep the machine busy. If the machine is kept busy doing useful work, I'm suggesting that that will lead to high performance. On the other hand, if the machine has idle periods, to the extent that it has idle periods, performance will be reduced. So our objective as the warp scheduler, we have the option, we have the opportunity to schedule instructions on execution units. And our objective is to keep this graph busy from left to right. So we're starting with a clean slate. We're starting in clock cycle C0. We have a bunch of warps that are ready to go. And I've depicted the instructions just as a memory aid in the upper right-hand corner of this slide, just a refresher from the last slide. It's the same three set of instructions. The GPU is an in-order machine, so we must issue instruction I0 before we can issue instruction I1, and likewise with I2. And that's true for each warp. Each warp must execute I0 before it can execute I1 and before it can execute I2. It's an in-order machine. So in clock cycle C0, we have a bunch of warps that are ready to go. Their instruction pointers all point at instruction I0. And as a warp scheduler, let's pretend that I have 32 execution units that I can schedule. So I can schedule 1 warp's worth of work. And I have what's depicted here, 10 warps to choose from. Does not matter which one I choose. So I'm going to choose warp 0, and I'm going to execute instruction I0 in clock cycle C0. And we're going to say the machine is busy at that point. In other words, the machine is fully occupied. We have done our work for clock cycle C0. And then I have a similar choice to make in clock cycle C1. Now, in clock cycle C1, I had some variability here because I could issue instruction I1 for warp 0, or I could have issued instruction I0 for a different warp. Those are two valid choices. No reason to choose one or the other. No specification to indicate which one will happen. The machine could make either choice. We're going to pick one for the purposes of instruction, and we're going to say the warp scheduler, that's us, chose to issue I1 in clock cycle C1 for warp 0. Now, I know that I can issue I1 because it's a load instruction, which is a memory read, and memory reads can never stall. They will never cause a warp to stall. So if I am looking through the warp instructions and I come across a load instruction and my instruction pointer is at that point, I know I can issue that instruction. I can always issue it. There is no possibility for that to cause a stall. But after issuing instructions I0 and I1 to warp 0, my next instruction is I2. Can I issue I2? Well, I can't because I0 and I1 are in flight still. In other words, I have issued those instructions, but the registers R0 and R1 are not yet populated with valid data because there is latency. Okay, and so when I issue the instruction, I've asked for this value, A of IDX, to be put into R0, but it's not done in a single clock cycle. There's latency. Therefore, if I get to an instruction that depends on R0 or R1, I know that they're not ready yet. And therefore, if I continue this process, this warp has stalled. Okay, so this warp cannot, at this point in time, in clock cycle C2, this warp cannot issue I2. So the warps, I'm the warp scheduler, I no longer have that option. Now what do I do? Well, no problem, I'll just go to another warp because I know that I can issue I0 for warp 1, for example. And likewise, I can issue I1 for warp 1. And then that warp will stall. And I can repeat this process. Okay? And so one possible path of execution that the warp scheduler might choose is to issue I0 and I1 to warp 0, then I0 and I1 to warp 1, and so on. And this process could continue as long as I have warps available. If I had an infinite number of warps, I could continue this process as long as I liked. Now, so far, I'm doing a pretty good job of satisfying my objective, because my objective in a nutshell is to keep the machine busy. And one of the ways that I could define that pictorially is to say that there is no clock cycle that is empty. Every clock cycle has an instruction issued in it. That's a good thing. That means the machine is doing something in every clock cycle. Okay? But eventually, one of two things will happen. Either I'll run out of warps, or eventually something else will happen. And the something else that will happen eventually is that the latency will become satisfied. So latency is not infinite. Eventually, the thing that I asked for will be delivered. And the very first thing that I asked for was for R0 of warp 0 to be populated with A of IDX, which might have been 0, for example, or whatever A is across, whatever IDX is across the warp. Nevertheless, at some point or another, the memory subsystem will deliver the value of A of IDX into R0 for each member of that warp 0. That's true for I0. It's also true eventually for I1. And so we can imagine at some point that our latency expires. And when the latency expires, a new thing is possible. The new thing that's possible is once warp 0 becomes unblocked due to latency, in other words, it's no longer stalled, then the warp scheduler has a new choice. The new choice is that it can issue instruction I2 into warp 0. And while it's doing that, because memory is a pipeline means, amongst other things, that if I ask for operation A in the pipeline in location 0 and operation B in location 1, the pipeline will have a fixed latency. That means that the result of operation A appears the latency cycles later, and the result of operation B appears the latency cycles plus 1 later in terms of clock cycles. So in the very next clock cycle, after getting the result loaded into R0, memory will load the result into R1. And in the very next clock cycle after that, for warp 1, R0 will be loaded. And in the very next clock cycle after that, for warp 1, R1 will be loaded. And so this operation that sort of stacked up and became stalled will also unstack and become unstalled in approximately the same order after the latency has expired. And so as a result of that, I can eventually issue the instruction I2 for warp 1. And as these things unstall, I can continue to issue instructions. Now, roughly speaking, the latency that I've depicted here from I0 in the upper left-hand corner to I2 in clock cycle 18 would be 18 cycles of latency. That's probably longer than your typical arithmetic latency, and it's probably a lot shorter than your typical global memory latency. So we should imagine that if all I was doing was a bunch of global memory operations, these things wouldn't be uninstalling in clock cycle 18. It would be sometime later, depending on the global memory latency. Now, that brings me to my next point, which is my first thought question. If you are a programmer, if you're the warp scheduler or the programmer, what can you do to optimize this scenario? What can you do to make this scenario have the best possible outcome? And the answer that I'm looking for is to make the vertical axis, the y-axis, longer. In other words, instead of having 10 warps, if I had 20 warps, I could go twice as far in this sequence before I would start to need some of these warps to unstall and to continue activity. Likewise, if I had 40 warps, I could go farther. If I had an infinite number of warps, this would be an awesome scenario because I could always keep the machine busy. But on the other hand, that would be an implication that I have infinite work to do. So that's really not a sensible design choice. It's not an option for GPU design or the GPU programmer. we do have a hardware limit to the number of warps that we can have open and ready to go on an SM. And for most SMs, that number is 64. Okay, for the Turing family, it's dropped down to 32. But for most of the SMs, for all of the architectures that we've talked about so far, Kepler to Volta, it's 64 warps. So this process that we have unveiled here is called latency hiding. The way that the machine hides the latency that we're talking about is the latency from I0 to I2 or I1 to I2 in the first warp. There's a big gap of empty space there that we had to wait before the operands were ready so that we could issue I2. That big gap is called latency. And if the only thing that we had was warp 0, there would be 18 cycles where the machine is doing nothing, just waiting. Okay? The way that we keep the machine busy is to have other warps to go to have other work to do, to have other instructions to issue. And that's how we keep the machine busy doing useful work during this gap that we call latency. This is the latency, this is the fundamental latency hiding process on the GPU, and it's fundamentally how the GPU delivers high performance in a massively thread parallel architecture, in spite of the fact that memory can and does present a significant latency to its requests. Okay. In fact, if I have an optimal scenario here, memory latency doesn't matter. In fact, most other latencies probably wouldn't matter either. When the GPU has effectively hidden latency, in other words, when you as the programmer have provided enough warps, then the GPU always has work to go to do, useful instructions to execute, instructions that were going to have to be executed sooner or later in order to get your work done. Okay, so one of the main takeaways, in fact, the main takeaway from this slide, our main observation is that we want to have a lot of threads. Or if you like, we could say we want to have a lot of warps. And to be more specific, we'd like to have a lot of warps per SM. In fact, we know what the upper bound is. We know what the best case scenario is. It's 64 warps per SM. And so we know that a warp is composed of 32 threads, so 64 times 32 is 2048. So we would like to have 2048 threads per SM. If I have 80 SMs in my machine, like a Volta processor, then I want 80 times 2048 is 160-some thousand threads. Therefore, if I write a CUDA kernel and my launch configuration is less than around 160,000 threads, I'm pretty confident, as your advisor, I'm pretty confident that you will not saturate a Volta processor. And the way to get the most performance out of the GPU, any GPU, is to saturate the GPU, to deliver enough threads so that the machine can be fully occupied and have the best opportunity for latency hiding. Therefore, if you write a CUDA code running on a Volta processor and you use 1,000 threads to realize the algorithm, and you observe that there's another way that I could realize this algorithm that would use 32,000 threads, there's a very good possibility that the 32,000 thread realization is going to run faster than the 1,000 thread realization. Very good probability on a Volta processor. Another final observation I'll make about this slide is that in this entire discussion, we haven't used the word cache. Latency hiding presumes to be able to do its work without the benefit of caches. Now, GPUs do have caches, but GPUs didn't always have caches. The very first architectural family, it was before, significantly before the Kepler family, but the very first compute-capable GPU family actually had no caches. And yet, people found it to be an interesting processor and did interesting things with it. And so this latency hiding operation, in theory, can hide any latency if you give the machine enough work to do. Caches, of course, may help with latency hiding by reducing the latency, reducing the time it takes to retrieve a value from memory. Okay, let's move on. So if we're hiding arithmetic latency, we can sort of imagine from the previous diagram, if we want to hide latency that's on the order of 5 to 10 cycles, then a diagram like what we talked about is probably enough. We got to a latency hiding, we got to a gap of around 18 cycles just with that description that I gave you across 10 warps. 10 warps is 320 threads. So if we have on the order of tens of warps per SM, like 10, 20, 30 warps, we probably are going to give that SM a good opportunity to hide arithmetic latency. But as we know already, global memory latency is much longer. So really we want as many threads as we can get, up to 2048 per SM. We also know that the machine is dual issue. We've said that already. That means that if two adjacent instructions in the instruction stream are not dependent on each other, it's possible that the warp scheduler can issue both of those instructions. And therefore, one of the beneficial characteristics to avoid stalls is to have instructions that are independent of each other, scheduled close together. In other words, grouped by the compiler close together. Now, so the GPU compiler is aware of this concept, and it will aggressively seek to do this. It will aggressively seek to put independent instructions early in the instruction stream so that we can get this GPU up and running. And so the GPU may very well do things like unroll loops and reorder instructions at compile time, reordering instructions that are independent of each other to early in the instruction issue sequence, early in the thread sequence. Okay, so it's not really something that you as a programmer should spend a lot of time worrying about. It's not a first-level optimization objective, but you should be aware that as you get into more complex optimization scenarios, things like loop unrolling may be something that starts to come into your parlance, something that you start to think about. We'll also want to maximize global memory throughput, and what we're going to observe is that there's a relationship. In fact, if you do the homework today, you may observe that there's a relationship between lots of threads or latency hiding or exposing parallelism, similar concepts. There's a relationship between those concepts and achievable memory bandwidth, global memory throughput. If you do the homework, it will walk you down that path. Okay? That concept really straddles the concept that we're going to learn today and the one that we're going to be learning in our next session. So in the homework, I refer to that as two sides of the same coin. Because when we make efficient use of the machine in terms of providing it a lot of exposed parallelism, we also give the machine a good opportunity to saturate memory, to fill its memory pipe. There are some things that we can do as a programmer to help this along. For example, if we can operate on larger chunks of data per thread, then we can fill up the memory pipe with a smaller number of threads and achieve the same level of memory saturation. Okay? Again, not a terribly important concept, but it's something to be aware of as you get farther into the optimization scenario. Right now, it's not a top-level optimization objective, but something that you may run into later is to do something called a vector load, for example. A vector load might load 4 float quantities per thread, and then that thread would do the operations on each of those 4 float quantities, and then store the results perhaps as a vector store. And in so doing, it would be loading 16 bytes per thread instead of 4 bytes per thread. So it would be a slightly different realization of the algorithm, loading more data per thread, and in some cases that can give a boost to your performance. Okay, so this slide is simply reflecting the same idea that if I load more data per thread, I can saturate the memory bus earlier. And by earlier, I mean with a smaller number of threads per multiprocessor. So really just graphically restating the concept that I was making at the bottom of the previous slide. Okay, so we're just about at the end of our lesson this week, and we want to summarize what we've learned. Remember, this is the first of the 2 concepts, what I'm going to call the top-level optimization priorities for any CUDA programmer, the things that if you keep in mind, you will be able to predictably write fast code. And our first concept that we've learned today, quite simply, is make sure you use a lot of threads. Whatever that means in terms of your algorithm realization and your design of your kernel launches, use lots of threads. Typically, we'd like to have at least 512 threads per SM, and really you should be aiming for 2048. There's no reason really to stop at 512, but what you may observe is significantly diminishing returns as you go from 512 to 2048. On the other hand, you may observe huge returns by going from 32 threads to 512 threads, for example. That could be easily an order of 2x to 10x performance difference in your code. And as you go from 512 to 2048 threads, you might observe another 20%, 40%, 60% performance increase. If you're processing smaller data per thread, you'd like to err on the larger side of that. Again, really no reason not to aim for 2048. And of course, these generalizations that we're making may not apply in every case. What we'll observe later in analysis-driven optimization in a subsequent lesson is that there are various limiters to performance in the GPU. And although latency is a very common limiter to performance, it's not the only one, and it's not always the one that is the actual limiter for your code. And so if your code is running into another limiter, you may observe that increasing the number of threads per SM, in other words, more threads, doesn't improve the performance of your code because your code is running up against another limiter. And analysis-driven optimization would be our standard recommendation for how you'd begin to unpack that, identify the limiter, and attempt to address it from a coding perspective. So exceptions can certainly exist. Another takeaway that we haven't mentioned up until now is that thread blocks should be a multiple of the warp size. The reason for this may or may not be obvious, but what I said was that instructions are always issued warp-wide. That means that instructions are always issued to 32 threads, whether you have 32 threads in the warp or not. A thread always has 32 threads. It may have some that are active, in other words, ones that you have defined in your thread block, and some that are inactive. Let's take an example. Let's say I defined my thread block to have 48 threads. So the second number in my launch configuration is 48 threads per block. That block is going to consist of 2 warps. The first warp has 32 threads in it. The second warp has 16 active and 16 inactive threads. When the warp scheduler is scheduling the first warp, it schedules it across 32 of the appropriate execution unit type. So if it's a load instruction, it chooses 32 load store units and deposits 1 operation per thread on each of the 32 load store units, and it services that instruction warp-wide that way. It does exactly the same thing with the second warp. Even though the second warp only has 16 active threads in it, 32 load store units would still be required. 16 of those load store units would be doing useful work, and 16 would be inactive. They would be occupied for a cycle, but they would be doing nothing useful. There is no other way to schedule instructions in a GPU. You can't schedule 1 instruction to 1 execution unit or 2 instructions to 2 execution units or anything like that. Instructions are always issued warp-wide. Therefore, if we have the choice, which usually we do, if we have the choice, it makes sense to make my thread block a whole number multiple of 32, so that every warp is operating in the most efficient way possible. For the 32 execution units that are scheduled per instruction in that warp, all 32 execution units are doing useful work. Okay. Sometimes it's inconvenient to choose a large number of threads per thread block, and so we can achieve our objective even with a smaller number of threads per thread block. For example, if I choose to have 512 threads in my thread block, something that we haven't talked about yet, but which I'm telling you now, is that an SM can have deposited on it more than 1 thread block. At the beginning of this discussion, we said, if I have 6 SMs in my GPU, I probably need to have at least 6 thread blocks to use those 6 SMs, which is true, but it's not the whole story. The whole story is that we'd like to have 2048 threads per SM. And some of you may have noticed that 2048 is greater than our maximum number of threads per block, which is 1024. So how do I get to 2048? Well, I get to 2048 by having multiple thread blocks deposited per SM. And so the warps that we depicted on our diagram may come from different thread blocks, no problem. There's no problem with that. The warp scheduler can handle that with no issues. And so one of the ways, in fact, the way that I would get to 2048 threads is to have at least 2 thread blocks per SM. And if I have a smaller number of threads per thread block, I might need more. So if I had 512 threads per thread block, because my launch configuration, 5 in the second position, then I would need 4 of those thread blocks. Okay, we want to avoid really small thread blocks because we get the large numbers of thread blocks that are needed. Really large thread blocks can also prevent achieving good occupancy, so a number like 512 tends to work pretty well. But I wouldn't worry too much about these statements that I'm making just now. Your objective is to make it possible so that 2048 threads can be deposited per SM. And that is very flexible and possible if you use numbers like 128, 256, or 512 for thread block size choices. I haven't really used the word occupancy too much, but you're going to run into it sooner or later. We will eventually talk about occupancy when we get to the section on analysis-driven optimization. But occupancy is a concept we can readily understand from what we've done so far. Namely, occupancy is a measure of the actual thread load on the SM versus the peak theoretical load. Now, I don't want to spend a lot of time diving into this right now, but we can already start to ascertain what some of these numbers might be. The actual thread load, if I have 6 SMs and 6 blocks, is nothing more than the threads that I have per block. The theoretical number, for now, we'll say is 2048. So if I launch 6 blocks on a GPU with 6 SMs, then the number of threads per block divided by 2048 is my occupancy. Okay. Now, occupancy, the actual calculation of occupancy can get a lot more complicated than that. There are other limiters to occupancy besides thread load, and therefore CUDA includes an occupancy calculator spreadsheet. It's part of the CUDA toolkit distribution. It's an Excel spreadsheet, and if you go in there and use that spreadsheet, you can figure out what your best case occupancy is for your kernel design. And of course, if you're getting to 100% occupancy, you're doing a good job. As I mentioned, occupancy can have other limiters besides thread load, but the first one is threads per thread block. That can be a limiter. Another one can be registers per thread. In other words, how many registers are needed for your thread. That can be a limiter to occupancy. That's determined by the compiler. And shared memory usage can also be a limiter to occupancy. So these are topics that we will possibly revisit later during analysis-driven optimization, but I wanted to give you a brief introduction to the idea of occupancy. So with that, we've learned that the GPU is a massively thread parallel latency hiding machine. We have learned that what we're focused on right now is that with the appropriate choice of kernel launch configuration, we want to launch enough threads per SM to hide latency, and we want to launch enough thread blocks to load the entire GPU. So with that, I'm at the end of my slides, and the slides include, these are some of our future sessions. The slides also include topics for further study, and the slides also include a description of the homework assignment, which is very similar to previous homework assignments. This homework assignment just has one problem. It's one problem where you'll write some code very similar to what you've done already, and then you will spend some time with the profiler. So this homework assignment is, again, introducing something new. The thing that it's introducing new is the profiler. You'll learn in a very simple way how to use a profiling tool called nSight Compute, and you will use nSight Compute to inspect performance with various different kernel launch configurations. And hopefully what you learn there will reinforce this idea that having lots of threads and being able to fill all of the SMs on your GPU are important determinants of performance. So with that, I'm at the end of my slides, end of my talk, and I will pause for questions. Unfortunately, my phone is starting to die, so if my audio stops, I will reconnect my audio using a different phone. We'll wait until that happens.
All right. I think there are a few questions in the chat if you want to check those out and see if anybody asks questions with their microphone afterward.
Okay. I'm just catching up on the chat again. Is there additional latency when doing operations in place? I don't really know what that means. The GPU is a load store architecture, so all operations are done out of registers with very few exceptions. I don't know what it means to say in place. Architecturally, can I think of warps within a block as SMT threads within a vector processing core? You can. A lot of people make that association. It's not a perfect one-to-one correspondence, but a SIMT architecture, people might say that a modern processor like x86 or Power 9 is a SIMD architecture when we're talking about vectorization. And so I can issue an instruction to a vector unit, and that instruction in those processor architectures will execute across a vector of data, and we would call that a SIMD style of programming, and we might call that SIMD vector extensions. Because we have this similar but slightly different concept of a warp with multiple threads, NVIDIA has coined the term SIMT, S-I-M-T, single instruction, multiple thread, to distinguish that it's a slightly different behavior between that and single instruction, multiple data. The difference in behavior is that threads can diverge, and we can have a portion of the warp doing one activity and a portion of the warp doing a different activity based on conditional code that I write. Okay. And that's one example of a slight difference between SIMT and SIMD architectures. But nevertheless, that's a reasonable association. Can we issue I0 at both W0 and W1 at the same cycle C0? You could if W0 and W1 were assigned to two different warp schedules. I don't remember if we talked about this, but an SM design has multiple warp schedulers. Modern SM designs do. Older GPUs might not have, but modern SM designs have multiple warp schedulers. And if I have multiple warp schedulers, then an instruction I0 for W0 could be issued by one warp scheduler, and I1 for W1 could be issued in the same cycle. And the assumption there is that I have enough underlying execution units to support that. So if I'm issuing a floating point multiply, and I have 64 floating point multiply units, SP units, then one warp could issue I0 and another warp could issue I0, but it would have to be two different warp schedulers in that case. Is there any negative impact of launching huge number of threads? Basically, no. As you will see time doing this, you can realize some algorithms with very large numbers of threads, and the GPU runs approximately the same as it would with just the right number of threads to keep the machine busy. There's generally very little difference. You're talking only a few percent. And so in this level of instruction where we're trying to make sure that you get the first 80 or 90% of performance and don't make a mistake that cripples you into getting 10% of the performance of the machine, we're not interested in going after the last few percent. There may be a small difference in launch configuration or performance of different launch configurations depending on large numbers of threads, but it's usually quite small, on the order of a few percent at most. Is there any difference between launching n warps per block versus half the number of warps per block on 2x as many blocks, aside from no shared memory? Generally, there shouldn't be much difference. Here's an example where there could be a difference. Let's say my GPU SM design is limited to 16 thread blocks. That's another hardware architectural limit that we didn't spend a lot of time talking about, but I did depict it on one of the slides. Let's say that my particular GPU SM design is limited to 16 thread blocks total. And let's say that I have 64 threads per block. Then 16 times 64 is, now let's say I cut that number of threads per block in half. 64 goes to 32. But I can launch twice as many thread blocks, no problem. but my GPU SM can still only hold 16. So now the maximum complement of threads that I can have is 16 times 32. Now I've reduced it to 512 thread load per SM. Example where it can bite you, but if you're up in the range of, let's say, 512 threads per block, then you'll generally find essentially no performance difference between launching 512 threads per block across 100 blocks, or let's say 1,000 blocks. No difference between that and 256 threads per block with 2,000 blocks. Generally speaking, though, that makes no difference in terms of GPU performance, because ultimately the thread complement per SM is likely to be the same. So with that, I think I have reached the end of the comments or the end of the question in the chat. And if there are more questions real time, we can handle those at this time.
All right. So if there are no other questions, and for the sake of Bob's battery on his phone, we should maybe stop there. I would like to thank Bob for his presentation and for answering our questions for us.